Hi, welcome to non-destructive testing subject. Today topic is Introduction to Non-Destructive Testing. Myself G. Sundar Raju. Assistant Professor. Mechanical Engineering. Baneri Amman Institute of Technology. Sathyamangalam. Tamil Nadu. Non-destructive testing, NDT, is the process of inspecting, testing, or evaluating materials, components, or assemblies for discontinuities, or differences in characteristics without destroying the serviceability of the part or system. In other words, when the inspection or test is completed, the part can still be used. Today modern non-destructive tests are used in manufacturing, fabrication, and in-service inspections to ensure product integrity and reliability, to control manufacturing processes, lower production costs, and to maintain a uniform quality level. Also, NDT plays a crucial role in everyday life and is necessary to assure safety and reliability.
X-rays are being used to examine the human body without invasive surgery. But did you know that similar methods are also being used to determine the health of machines or structures? Methods that examine something without causing harm to it fall under the general term of non-destructive testing, or NDT for short. It is used to quickly evaluate materials in a component or a system, let's say a bridge, without tearing it apart, rendering it unusable for a very long time. One popular testing method works a little bit like getting an X-ray and is called radiography. To understand how it works, we need to have a quick look at electromagnetic radiation. Electromagnetic radiation can be described as a stream of particles without a real size, called photons, each travelling in a wave-like pattern in various wavelengths at the speed of light. You may already know more about it than you might think. Radio waves, microwaves, but also the light visible to the human eye. That's all electromagnetic radiation which can be categorised in the electromagnetic spectrum. To be able to examine the inner workings of an object in detail, we need to look at the part of the spectrum with the shortest wavelengths. It's here where we can find X-rays and gamma rays. Unlike visible light, X and gamma ray beams can be sent through most objects while a part of them will be absorbed, depending on the object's density and composition. The rays that pass through the object are then captured by a detector, like a photographic film, creating a radiograph. This is only one of the many methods of non-destructive testing, but why is it so important? These testing methods can not only evaluate the property of material used in an object, but also detect flaws that might otherwise cause a lot of trouble. That's the reason why the IAEA is promoting the use of radiation-based non-destructive testing by helping its member states train staff in applying the technology, as well as providing necessary equipment. It is also providing know-how for analysing paintings and other cultural heritage artefacts, but that's a whole other story. Thanks for watching, and if you want to know more about non-destructive testing, please click on one of the links next to the video or go to our website.
Manufacturing can be defined as the process of converting raw material into a usable form of products, or goods for human needs. The important types of manufacturing process are 1. Welding, 2. Casting, 3. Forging, 4. Machining. Manufacturing is the production of goods through the use of labor, machinery, tools, and biological or chemical processing or formulation. Manufacturing can either mean transforming raw materials into finished goods on a large scale, or the creation of more complex items by selling basic goods to manufacturers for the production of items such as automobiles, aircraft, or household appliances. NDT is used to ensure the quality of materials and joining processes during the fabrication and erection phases, and in-service NDT inspections are used to ensure that the products in use continue to have the integrity necessary to ensure their usefulness and the safety of the public. Why are metals tested? Ensure quality. Test properties. Prevent failure in use. Make informed choices in using materials. Factor of safety is the ratio comparing the actual stress on a material and the safe usable stress. Manufacturing defects. A defect is defined as a flaw is render a part or product unable to meet minimum applicable acceptance standards or specifications. It should be clear that a discontinuity is not necessarily a defect. There are three types of product defects. Design defects occur before a product is manufactured because the product was either not tested properly, or poorly designed. Every item that is produced using the flawed design is considered dangerous. Manufacturing defects happen when an error in the manufacturing process deviates from the intended design. Warning defects hold the manufacturer, supplier, or vendor responsible for inadequate warning labels or instructions for use on a product. Defects are common in any type of manufacturing, welding including. In the process, there can be deviations in the shape and size of the metal structure. It can be caused by the use of the incorrect welding process or wrong welding technique. So below we'll learn about the 7 most common welding defects, their types, causes, and remedies. Undercut. This welding imperfection is the groove formation at the weld toe, reducing the cross-sectional thickness of the base metal. The result is the weakened weld and workpiece. Causes. Undercut. Too high weld current. Too fast weld speed. The use of an incorrect angle, which will direct more heat to free edges. Porosity. Porosity occurs as a result of weld metal contamination. The trapped gases create a bubble-filled weld that becomes weak and can with time collapse. Incomplete fusion. This type of welding defect occurs when there's a lack of proper fusion between the base metal and the weld metal. It can also appear between adjoining weld beads. This creates a gap in the joint that is not filled with molten metal. Causes. Incomplete fusion, low heat input. Surface contamination. Electrode angle is incorrect. Causes of porosity. Porosity, inadequate electrode deoxidant. Using a longer arc. The presence of moisture. Spatter. Spatter occurs when small particles from the weld attach themselves to the surrounding surface. It's an especially common occurrence in gas metal arc welding. No matter how hard you try, it can't be completely eliminated. However, there are a few ways you can keep it to a minimum. Causes. Spatter, the running amperage is too high. Voltage setting is too low. The work angle of the electrode is too steep. Lack of fusion and incomplete penetration. Lack of fusion is another serious weld defect which can occur as a result of a lack of fusion between the weld metal and the parent metal at the root of the weld when complete penetration is required. A lack of sidewall fusion which occurs between weld metal and parent metal at a side weld outside of the root of the weld. A lack of inter-run fusion which occurs between adjacent layers of weld metal on a multi-run welds. Excess reinforcement or penetration. For butt welds is excess weld metal above the height of the parent metal or excess weld metal protruding through the root side of a weld made from one side of the joint. For fillets is excess weld metal above the specified fillet size including throat thickness. Excess reinforcement/penetration can be caused by excessive current, too slow travel speeds and incorrect joint fit up. Casting defects are 1. Gas porosity, blowholes, open holes, pinholes. 2. Shrinkage defects, shrinkage cavity. 3. Mold material defects, cut and washes, swell, drops, metal penetration, rat tail. 4. Pouring metal defects, cold shut, misrun, slag inclusion. 5. Metallurgical defects, hot tears, hot spot. Blowholes. When gases entrapped on the surface of the casting due to solidifying metal, a rounded or oval cavity is formed called as blowholes. These defects are always present in the cope part of the mold. Causes. Excessive moisture in the sand. Low permeability of the sand. Sand grains are too fine. Too hard rammed sand. Slag inclusion. This defect is caused when the molten metal containing slag particles is poured in the mold cavity and it gets solidifies. Causes. I. The presence of slag in the molten metal. Remedies. I. Remove slag particles from the molten metal before pouring it into the mold cavity. Hot tears or hot cracks. When the metal is hot it is weak and the residual stress, tensile, in the material cause the casting fails as the molten metal cools down. The failure of casting in this case looks like cracks and called as hot tears or hot cracking. Causes: I. Improper mold design. Remedies: I. Proper mold design can easily eliminate these types of casting defects. 2. Elimination of residual stress from the material of the casting. Hot spot or hard spot. Hot spot defects occur when an area on the casting cools more rapidly than the surrounding materials. Hot spot are areas on the casting which is harder than the surrounding area. It is also called as hard spot. Causes: I. The rapid cooling an area of the casting than the surrounding materials causes this defect. Remedies: I. This defect can be avoided by using proper cooling practice. 2. By changing the chemical composition of the metal. Defects in forging. Though the forging process provides good quality products compared to other manufacturing processes, some defects that are likely to come if proper care is not taken in forging process. Cold shut. Short cracks at corners and at right angles to the surface of forging. It is caused due to metal surface folding against itself during forging. This appears as small cracks at the corners of the forging. Scale pits are seen as irregular deputations on the surface of the forging that is caused primarily due to improper cleaning of the stock used for forging. The oxide and scale get embedded into the finish forging surface. Flakes. These are basically internal ruptures caused by the improper cooling of the large forging. Rapid cooling causes the exterior to cool quickly, causing internal fractures. This can be remedied by following proper cooling practices. Improper grain flow. This is primarily caused by the improper design of the die that induces material flow in an inappropriate manner, leading to various defects. Testing generally means to manually test/break the application so as to find flaws or defects in it, so that when it is rolled out for production, our customers/any users will not have any issue with the product. Inspection is a process of reviewing anything which is documented and which was used as a base to carry out testing. For example, test cases, test scenarios, requirement review. Inspection helps in finding defects at an early stage. Destructive testing, DT, is a form of object analysis that involves applying a test to break down a particular material to determine its physical properties, such as the mechanical properties of strength, toughness, flexibility, and hardness. Types of destructive testing are: tensile test, compression test, hardness test, impact test, further categorized as Charpy test and ISAD test, bend test, fatigue test, corrosion resistance test, wear test. Non-destructive testing, NDT, has been defined as comprising those test methods used to examine an object, material, or system without impairing its future usefulness. The term is generally applied to non-medical investigations of material integrity. Non-destructive testing types are: visual testing, die penetrate inspection, magnetic particle inspection, radiographic testing, ultrasonic testing, leak testing, eddy current testing. A wide group of analysis techniques used in science and industry to evaluate the properties of a material, component, or system without causing damage. Non-destructive examination, NDE. Non-destructive inspection, ND. Non-destructive evaluation, NDE. Non-destructive testing involves techniques based on application of physical principles employed for purpose of determining characteristics of materials or components and for detecting and assessing inhomogeneity and harmful defects without changing the usefulness of materials or components. The methods used may be simple or intricate. It plays a vast role in quality control of finished product. Skill, judgments and experience is required while performing NDT. Typical examples are found in aircraft, spacecraft, shuttle, motor vehicles, pipelines, bridges, trains, power stations, refineries, buildings. Non-destructive testing, NDT, is an interdisciplinary science that uses many different methods to evaluate the properties of metals, parts, or assemblies without causing damage to the tested part or assembly. Because no damage results from these testing techniques, it is often done as part of the manufacturing process to determine if any flaws are present or created. It is also often used for product evaluation or during failure analysis. NDT applications areas are aerospace engineering, mechanical engineering, electrical engineering, electronics engineering, civil engineering, systems engineering, food industry, sports, power plants, chemical plants. Importance of NDT: safety and reliability, reduce the cost of product, reputation, elimination of forced shutdown, accident prevention and to reduce costs, to improve product reliability, to determine acceptance to a given requirement, to give information on repair criteria. Current NDT methods are acoustic emission testing, AE, electromagnetic testing, ET, laser testing methods, LM, leak testing, LT, magnetic flux leakage, MFL, liquid penetrant testing, PT, magnetic particle testing, MT, radiographic testing, RT, thermal/infrared testing, IR, ultrasonic testing, UT, vibration analysis, VA, and visual testing, VT. The 6 most frequently used test methods are MT, PT, RT, UT, ET, and VT. Each of these test methods will be described here, followed by the other, less often used test methods. Visual testing is the most commonly used test method in industry. Because most test methods require that the operator look at the surface of the part being inspected, visual inspection is inherent in most of the other test methods. As the name implies, VT involves the visual observation of the surface of a test object to evaluate the presence of surface discontinuities. VT inspections may be by direct viewing, using line-of-sight vision, or may be enhanced with the use of optical instruments such as magnifying glasses, mirrors, buroscopes, charge-coupled devices, CCDs, and computer-assisted viewing systems, remote viewing. Corrosion, misalignment of parts, physical damage, and cracks are just some of the discontinuities that may be detected by visual examinations. Types of visual testing: direct visual testing, remote visual testing. Tools include fiberscopes, borescopes, magnifying glasses, and mirrors. Portable video inspection unit with zoom allows inspection of large tanks and vessels, railroad tank cars, sewer lines. Visual inspection: the inspector's vision, the amount of light falling on the specimen, the capability to process the visual data, the level of training and attention to detail. Principle: illumination of the test specimen with the light. Also requires proper eyesight of the tester. Surface of the test specimen should be cleaned before inspection, where test specimen is illuminated and inspected using naked eye or with the help of optical aids such as mirrors, magnifying glasses, microscopes or video cameras. The basic principle of liquid penetrant testing is that when a very low viscosity, highly fluid, liquid, the penetrant, is applied to the surface of a part, it will penetrate into fissures and voids open to the surface. Once the excess penetrant is removed, the penetrant trapped in those voids will flow back out, creating an indication. Penetrant testing can be performed on magnetic and non-magnetic materials, but does not work well on porous materials. Penetrants may be visible, meaning they can be seen in ambient light, or fluorescent, requiring the use of a black light. When performing a PT inspection, it is imperative that the surface being tested is clean and free of any foreign materials or liquids that might block the penetrant from entering voids or fissures open to the surface of the part. After applying the penetrant, it is permitted to sit on the surface for a specified period of time, the penetrant dwell time, then the part is carefully cleaned to remove excess penetrant from the surface. When removing the penetrant, the operator must be careful not to remove any penetrant that has flowed into voids. A light coating of developer is then be applied to the surface and given time, developer dwell time, to allow the penetrant from any voids or fissures to seep up into the developer, creating a visible indication. Following the prescribed developer dwell time, the part is inspected visually, with the aid of a black light for fluorescent penetrants. Most developers are fine-grained, white talcum-like powders that provide a color contrast to the penetrant being used. Advantages: high sensitivity to small surface discontinuities. Easy inspection of parts with complex shapes. Quick and inexpensive inspection of large areas and large volumes of parts/materials. Few material limitations: metallic and non-metallic, magnetic and non-magnetic, and conductive and non-conductive can all be inspected. A visual representation of the flaw are indicated directly on the part surface. Aerosol spray cans make the process portable, convenient, and inexpensive. Disadvantages: detects flaws only open to the surface. Materials with porous surfaces cannot be examined using this process. Only clean, smooth surfaces can be inspected. Rust, dirt, paint, oil and grease must be removed. Metal smearing from power wire brushing, shot blasting, or grit blasting must be removed prior to liquid penetrant examination. Examiner must have direct access to surface being examined. Surface finish and roughness can affect examination sensitivity. How does magnetic particle inspection work? A ferromagnetic test specimen is magnetized with a strong magnetic field created by a magnet or special equipment. If the specimen has a discontinuity, the discontinuity will interrupt the magnetic field flowing through the specimen and a leakage field will occur. Magnetic particle examination, MT, is a very popular, low-cost method to perform non-destructive examination, NDE, of ferromagnetic material. Magnetic particle testing. The part is magnetized. Finely milled iron particles coated with a dye pigment are then applied to the specimen. These particles are attracted to magnetic flux leakage fields and will cluster to form an indication directly over the discontinuity. This indication can be visually detected under proper lighting conditions. The magnetic particles may be a dry powder or suspended in a liquid solution, and they may be colored with a visible dye or a fluorescent dye that fluoresces under an ultraviolet light. Basic steps involved. Component pre-cleaning. Introduction of magnetic field. Application of magnetic media. Remove excess particle. Interpretation of magnetic particle indications. Demagnetization. Inspecting a test part is essential for the particles to have an unobstructed path for migration to both strong and weak leakage fields alike. The part's surface should be clean and dry before inspection. The required magnetic field can be introduced into a component in a number of different ways. Using a permanent magnet or an electromagnet that contacts the test piece. Flowing an electrical current through the specimen. Flowing an electrical current through a coil of wire around the part or through a central conductor running near the part. Detection of magnetic field. Two general types of magnetic fields, longitudinal and circular, may be established within the specimen. The type of magnetic field established is determined by the method used to magnetize the specimen. MPI can be performed using either dry particles, or wet method. Dry method. The dry method, the particles are lightly dusted onto the surface. The dry method is more portable. Wet method. Wet method, the part is flooded with a solution carrying the particles. The wet method is generally more sensitive since the liquid carrier gives the magnetic particles additional mobility. Interpretation. After applying the magnetic field, indications that form must be interpreted. This process requires that the inspector distinguish between relevant and non-relevant indications. After applying the magnetic field, indications that form must be interpreted. This process requires that the inspector distinguish between relevant and non-relevant indications. Demagnetization. Parts inspected by the magnetic particle method may sometimes have an objectionable residual magnetic field that may interfere with subsequent manufacturing operations or service of the component. Possible reasons for demagnetization include: may interfere with welding and or machining operations. Can affect gauges that are sensitive to magnetic fields if placed in close proximity. Abrasive particles may adhere to components' surface and cause an increase in wear to engines' components, gears, bearings, etc. Eddy current testing. Eddy current testing is particularly well suited for detecting surface cracks but can also be used to make electrical conductivity and coating thickness measurements. Here a small surface probe is scanned over the part surface in an attempt to detect a crack. Electromagnetic testing is a general test category that includes eddy current testing, alternating current field measurement, ACFM, and remote field testing. While magnetic particle testing is also an electromagnetic test, due to its widespread use it is considered a standalone test method rather than an electromagnetic testing technique. All of these techniques use the induction of an electric current or magnetic field into a conductive part, then the resulting effects are recorded and evaluated. Eddy current testing uses the fact that when an alternating current coil induces an electromagnetic field into a conductive test piece, a small current is created around the magnetic flux field, much like a magnetic field is generated around an electric current. The flow pattern of this secondary current, called an eddy current, will be affected when it encounters a discontinuity in the test piece, and the change in the eddy current density can be detected and used to characterize the discontinuity causing that change. Alternating current field measurement, ACFM, uses a specialized probe that introduces an alternating current into the surface of the test piece, creating a magnetic field. In parts with no discontinuities this field will be uniform, but if there is a discontinuity open to the surface, the magnetic field will flow around and under the discontinuity, causing a disruption of the field that can be detected by sensors within the probe. The resulting feedback can then be fed to software that can determine the length and depth of the discontinuity. There are three characteristics of the specimen that affect the strength of the induced eddy currents: the electrical conductivity of the material, the magnetic permeability of the material, the amount of solid material in the vicinity of the test coil. The strength of the eddy currents changes the electrical impedance, Z, of the coil. Ultrasonic testing. Ultrasonic waves are introduced into a material where they travel in a straight line and at a constant speed. At surface interfaces some of the wave energy is reflected and some is transmitted. The amount of reflected or transmitted energy can be detected and provides information about the size of the reflector. The travel time of the sound can be measured and this provides information on the distance that the sound has traveled. Ultrasonic testing is a very versatile inspection method, and inspections can be accomplished in a number of different ways. Ultrasonic inspection techniques are commonly divided. Pulse echo and through transmission. Relates to whether reflected or transmitted energy is used. Normal beam and angle beam. Relates to the angle that the sound energy enters the test article. Ultrasonic testing, UT, uses high-frequency sound energy to conduct examinations and make measurements. Ultrasonic inspection can be used for flaw detection/evaluation, dimensional measurements, material characterization, and more. UT is based on the capture and quantification of either the reflected waves, pulse echo, or the transmitted waves. Each of the two types used in certain application. Generally pulse echo system is more useful. UT inspection system consists of several functional units, such as the pulsar/receiver, transducer, and display devices. A pulsar/receiver is an electronic device that can produce high-voltage electrical pulses. Driven by the pulsar, the transducer generates high-frequency ultrasonic energy. The sound energy is introduced and propagates through the materials in the form of waves. When there is a discontinuity, such as a crack, in the wave path, part of the energy will be reflected back from the flaw surface. The reflected wave signal is transformed into an electrical signal by the transducer and is displayed on a screen. In the applet below, the reflected signal strength is displayed versus the time from signal generation to when echo was received. Signal travel time can be directly related to the distance that the signal traveled. From the signal, information about the reflector location, size, orientation, and other features can sometimes be gained. Radiography. The radiation used in radiography testing is a higher energy, shorter wavelength version of the electromagnetic waves that we see as visible light. The radiation can come from an X-ray generator or a radioactive source. Industrial radiography involves exposing a test object to penetrating radiation so that the radiation passes through the object being inspected and a recording medium placed against the opposite side of that object. For thinner or less dense materials such as aluminum, electrically generated X-radiation, X-rays, are commonly used, and for thicker or denser materials, gamma radiation is generally used. Gamma radiation is given off by decaying radioactive materials, with the two most commonly used sources of gamma radiation being iridium-192, IR-192, and cobalt-60, CO-60. IR-192 is generally used for steel up to 2-1/2, 3 inches, depending on the Curie strength of the source, and CO-60 is usually used for thicker materials due to its greater penetrating ability. Film radiography uses a film made up of a thin transparent plastic coated with a fine layer of silver bromide on one or both sides of the plastic. When exposed to radiation, these crystals undergo a reaction that allows them, when developed, to convert to black metallic silver. That silver is then fixed to the plastic during the developing process, and when dried, becomes a finished radiographic film. To be a usable film, the area of interest, weld area, etc., on the film must be within a certain density, darkness, range and must show enough contrast and sensitivity so that discontinuities of interest can be seen. These items are a function of the strength of the radiation, the distance of the source from the film and the thickness of the part being inspected. If any of these parameters are not met, another exposure, shot, must be made for that area of the part. Digital radiography, DR, digitizes the radiation that passes through an object directly into an image that can be displayed on a computer monitor. The three principal technologies used in direct digital imaging are amorphosilicon, charge-coupled devices, CCDs, and complementary metal oxide semiconductors, CMOSs. These images are available for viewing and analysis in seconds compared to the time needed to scan in computed radiography images. The increased processing speed is a result of the unique construction of the pixels, an arrangement that also allows a superior resolution than is found in computed radiography and most film applications. Radiographic images are shown in figure. NDT selection of process depends on nature of discontinuities, size and type, geometry, surface condition, component material and application, size and position, equipment and expertise available, cost, number of components to be tested. These are NDE application at almost any stage in the production or life cycle of a component. To assist in product development. To screen or sort incoming materials. To monitor, improve, or control manufacturing processes. To verify proper processing such as heat treating. To verify proper assembly. To inspect for in-service damage. Power plant inspection. Periodically, power plants are shut down for inspection. Inspectors feed eddy current probes into heat exchanger tubes to check for corrosion damage. Wire rope inspection. Electromagnetic devices and visual inspections are used to find broken wires and other damage to the wire rope that is used in chairlifts, cranes and other lifting devices. Storage tank inspection. Robotic crawlers use ultrasound to inspect the walls of large above-ground tanks for signs of thinning due to corrosion. Cameras on long articulating arms are used to inspect underground storage tanks for damage. Aircraft inspection. Non-destructive testing is used extensively during the manufacturing of aircraft. NDT is also used to find cracks and corrosion damage during operation of the aircraft. A fatigue crack that started at the site of a lightning strike is shown below. Jet engine inspection. Aircraft engines are overhauled after being in service for a period of time. They are completely disassembled, cleaned, inspected, and then reassembled. Fluorescent penetrant inspection is used to check many of the parts for cracking. Pressure vessel inspection. The failure of a pressure vessel can result in the rapid release of a large amount of energy. To protect against this dangerous event, the tanks are inspected using radiography and ultrasonic testing. Rail inspection. Special cars are used to inspect thousands of miles of rail to find cracks that could lead to a derailment. Bridge inspection. The US has 578,000 highway bridges. Corrosion, cracking and other damage can all affect a bridge's performance. The collapse of the Silver Bridge in 1967 resulted in loss of 47 lives. Bridges get a visual inspection about every 2 years. Some bridges are fitted with acoustic emission sensors that listen for sounds of cracks growing. Pipeline inspection. NDT is used to inspect pipelines to prevent leaks that could damage the environment. Visual inspection, radiography, and electromagnetic testing are some of the NDT methods used. Special measurements. Boeing employees in Philadelphia were given the privilege of evaluating the Liberty Bell for damage using NDT techniques. Eddy current methods were used to measure the electrical conductivity of the bell's bronze casing at various points to evaluate its uniformity. References. 1 Baldev Raj, Jayakumar, Thevasimathu M., Practical Non-Destructive Testing, Narosa Publishing, 1997. 2 M.C. Gonagal, Non-Destructive Testing, McGraw-Hill Books CO, 1988. 3 Barry Hull and Vernon John, Non-Destructive Testing, Macmillan, 1989. Thank you.